Hello everyone, my name is Ali Reza Ismail-Zahi, and today I'm going to present ZFusion efficient deep compositional zero-shot learning for blind image super resolution with generative diffusion prior, authored by me, Hossein Zaredar, Yapeng Tian, and Lale Sayed Kalantari. So first of all, we will have motivation, then methodology, results of our scheme, and finally the conclusion of this presentation. Starting from motivation. Diffusion-based image super-resolution schemes have provided SOTA performances thanks to the very strong image generation capability. They often use textual prompts like, for example, high quality, low quality, in order to provide superior results. And those some of those text prompts are related to degradation processes. But the challenge is that degradation processes at inference are often complex and unknown. In this work, we use compositional zero-shot learning, and we argue that basically we can decompose the unknown degradation embeddings as the combination of learned degradation attributes that are absolutely learned during the training process. So in this figure, actually, we visualize our motivation in subfigure B. As we can see in this subfigure, the unknown degradation attribute, which is shown by green, can be represented as the linear combination of 4 learned degradation attributes, 2 of them blue, 2 of them orange. Now we go to implementation. So during the training, we obtain the low resolution image from the ground truth using the synthetic degradations. As we can see, we have 2 modules, SDAL and RDAL. So basically in the SDAL, we obtain the textual embeddings S, which is obtained from the clip text encoder and synthetic degradation parameters. And in RDAL, we obtain the textual embedding F2, which is obtained again by clip text encoder, but with real world degradation embeddings obtained by IQA values. And then, because both of these 2 feature embeddings, F2 and S, are related to a single LR image, we apply alignment between them by the alignment loss. And then finally, we fine-tune clip vision encoder to obtain 2 sets of embeddings, F1 and F3, each of them aligned with the feature embeddings S and F2 respectively. After obtaining these degradation attributes, we incorporate them in our diffusion-based SR scheme, which has 2 stages. Stage number 1, image degradation suppression, and stage number 2, diffusion prior. In stage number 1, we use a transformer-based network and incorporate our degradation embedding as the feature modulation as seen in this figure. In stage number 2, we incorporate our degradation embeddings in a control net of a diffusion-based image super resolution scheme. So the results of ablation studies show that all the 2 modules, RD and SDAL, and also their alignment are indeed effective for providing superior super resolution performances. Here we show the results of our method and compare it with the other SOTA schemes on the Diff2K validation set, which basically the images are obtained by synthetic degradation operations. As we can see in most of the metrics, we can provide superior results. And also, in order to show our generalization capability to real-world unknown degradations, we show our results here on the real SR dataset, which again, our scheme is able to outperform the other SOTA methods, which most of them are diffusion-based. So here in this figure, we show the visual quality figures, which basically it is seen from both of the figures that our scheme is able to provide more realistic textures and also sharper structures. As a conclusion here in this work, we have presented a compositional zero-shot learning-based scheme for image super resolution, and we target improving the generalization capability of SR schemes to the case of unknown real-world degradations. Thank you very much.